Welcome everyone to our Hatch live webinar. My name is Ankush Bhagat, and on behalf of Hatch, I would like to thank you for joining us today on the topic demonstrating how NewCalc can effectively design and optimize a pneumatic conveying system for the cement industry. Before we officially commence, I would like to go over a few logistics. This webinar will be recorded and made available on our Hatch website, so you can watch it again or share it with your colleagues and friends. The session will last for 60 minutes. You should see 3 windows on your screen: a video, slide, and Q&A window. You can maximize or minimize these windows for better visibility. We encourage you to ask questions by entering your questions in the Q&A window throughout the webinar. Our speakers will get to as many questions as they can during this live demo. You will be prompted at the end of the session with a survey. Your comments are important to us so we can improve and expand our future webinars. So, without any further delay, it's my privilege to hand over to our host, Manoj Nigam, our mechanical discipline lead at Hatch. Over to you, Manoj.
Thank you, Ankush, for the introduction. Hi, everyone. Before I start introducing myself, let me just caution you that in case if there is some interruption because of the internet network, please have patience. We'll again restore that quickly. Hi, everyone. My name is Manoj Nigam, and I'm mechanical and piping lead in Hatch. And I've been in the industry for last 26 years. And during those 26 years, I worked in industries like continuous process plant, metal and mining, and some of the engineering consultancies. I've also visited some different countries like US, Canada, Australia, just to witness their good engineering practices. So it's my pleasure to welcome all of you around the globe in this live webinar showcasing NewCalc 7.0 software for designing and optimizing pneumatic conveying systems. We recently launched this particular software, and you know that it has got loads of crucial features which are essential when it comes to designing your pneumatic conveying system, whether it is under pressure, whether it is under vacuum, whether it is dense phase, whether it is dilute phase. So these all things would be there in this NewCalc 7.0 software. So let's get started. Let me share the agenda with you. So our agenda would be today I'll first introduce you with our key presenters. That will be followed by a demo with Jack, Hilbert, and Colin. I think that will take some around 30 minutes. Then once the demo is over, we'll try to take some of your questions. I believe we have dedicated somewhere around 15 minutes for that. And there would be handouts and survey would be available. And recording will also be available for that. So, and we also will provide you the promo code, and how we are going to use it, I'll tell you towards the end. So that's what the agenda is for today. Okay, so let me just start with introducing our key presenters. So first, I would like to introduce our key presenter, Mr. Jack Hilbert. Guys, I'll read his introduction so that I don't miss any of his important quality. Jack is our subject matter expert when it comes to pneumatic conveying. He is an extremely accomplished professional with 48 years of engineering, project management, and operation experience in the field of pneumatic conveying, bulk materials handling, dust collection, packaging, storage, distribution, terminals, and material processing. Jack has a bachelor's and master's degree in engineering from Penn State University and is a registered professional engineer. Next, we have Colin Barbeau, a bulk material handling specialist and a demo master today. So Colin will be handling this software. He will be controlling the software as Jack explains how it works. Colin is a mechanical engineer at Hatch, and he has been working in the bulk materials handling specialized technical team for more than 15 years. Colin is results driven and oriented towards system definition, equipment selection and design, equipment upgrade and rework, conceptual and feasibility studies, layout, and commissioning. So that's all about our key presenters. Now, without any further delay, I'll pass the floor to Jack, who will showcase you that how this NewCalc software is going to work for you in detail. Over to you, Jack.
Thank you, Manoj. Good morning, everyone, and good afternoon or good evening relative to your location. I would also like to extend my gratitude and thanks for you joining us today to hear more about the NewCalc 7 capabilities and how we can be used not only to design new systems for your applications and your plant, but more importantly, it can be used as a troubleshooting tool to help you analyze existing systems which may be having operational problems, performance problems, or to give you a chance to debottleneck and optimize existing systems to increase performance, increase the capacity of the system, or to reduce energy consumption. These are all different aspects of your system design and operation, which NewCalc can help you improve on a regular basis. NewCalc is a computerized program based on the original theory and work of Dr. Zenz. We've used his basic research work and application knowledge and research knowledge in developing the NewCalc program. If we go to the slide on slide number 5 that you're looking at now, we've actually set this demonstration up in the same format, in the same step-by-step procedure that we recommend you address a pneumatic conveying problem and a thought process to use as a guide. So the first thing we would always do is to take a sheet of paper and write down the key parameters that you're going to need to know, not only to design your system, but also to enter into the NewCalc program so we can do as computations in a logical, systematic manner. The information we're looking at are things like the particle size, the density of the material, the rate that you want to have your system designed for. And these are all the normal types of information that you should have available to you before you would start doing any type of calculation. So there's nothing out of the norm. During the presentation, Colin will be showing you exactly where this information is entered into the program and describe how it's used in the calculation process. The next slide looks at the different modes of conveying which are available. And when we talk about mode, we think about those terms that Manoj used in his introduction. NewCalc has the capability of designing systems and analyzing systems in all 3 modes of conveying: dilute phase, a 2-phase flow or mixed phase, as we refer to it in the program, and dense phase conveying. It's always a difficult decision to decide which mode of conveying you're going to try to accomplish in your specific case application. In the case we're looking at today, in the cement industry, we know that finished cement can be an abrasive material, causing wear in the pipeline. So one of the characteristics of dilute phase conveying is that it typically runs at a very high velocity, which means if you are handling something abrasive, it's going to generate more wear in the system. So we don't necessarily want to do our system design strictly in dilute phase conveying. If we look at the other end of the spectrum, in the lower right-hand corner, you see the diagram of dense phase conveying, or having slugs in the pipeline. That's used for a material which is abrasive because the velocity is very slow, the mass loading is very high in the system, but it's very dependent upon a very consistent material collection of properties. And we know that in the cement industry, we manufacture different grades of cement, different blends of cement size, different composition of additives, and we don't always have a true consistency of the material. So to eliminate the risk of not achieving our results, we're not going to go for the pure dense phase design. We're going to target a mixed phase or a 2-phase system, which is illustrated in the middle slide to the middle diagram to the right, where you see we have some dilute phase conveying taking place in the top of the pipe, but we have a more denser fluidized stream taking place in the bottom of the pipe. And the icon to the left on this slide is simply the phase diagram, which plots velocity versus pressure drop. And this is exactly what the fundamental purpose of NeuCalc is to analyze your application using a phase diagram approach, calculating pressure drops throughout the system from the beginning of the system at the point where the material enters the pipeline to the destination point where the material and air begin to separate, and product will drop out into your receiving station, and the air typically will then be discharged to atmosphere. You notice there's a color coding system where we look at the phase diagram and we see a blue color to the left, which is a dense phase regime. We look to the right side and we see a green color, and in between is a yellow color. This color coding system is carried out all the way through the NeuCalc program, and you'll see in Colin's demonstration how that color code is used to let you know when you are in your targeted range of two-phase flow or mixed phase conveying, or if you have gone into either dilute or dense phase conveying. The next question we have to ask ourselves is, what type of system do we want to design? And the next slide shows you that we've chosen a pressure system. Typically, we have two choices, a vacuum system or a pressure system. And there's lots of different factors that go into that analysis. But basically, in the cement industry, we're talking about usually high capacities. We're talking about relatively long conveying distances. And these are both characteristics of the need for a pressure type conveying system. One of the key elements of a pressure system is the line charger, and that's the piece of equipment that actually delivers the material from the source into the pneumatic convey line, not only at a controlled flow rate, but also typically against a pressure differential. In our demo today, we're going to look at two alternatives for those line chargers, and I'll discuss those in a moment. The next primary bit of information that we need to have available is the convey line geometry. And if we look at the next slide, you'll see that our example today is going to be based on a conveying system from the finish mill area over to a pair of loadout silos, and we're going to have a horizontal segment in the conveying system and a vertical segment and a number of bends. And one of the unique features about NeuCalc is that it lets you analyze your system exactly the way the pipeline geometry is run. Many other pneumatic conveying calculations simply look at a total distance of pipe or a total split between vertical and horizontal and number of bends. But the accuracy of the system design is much better when you can look at each segment as it's installed and analyze the pressure drop and velocity profile through each of those systems. And that's exactly what NeuCalc 7 does. And Colin will show you that in detail during the demo. And finally, we look at the next slide, which are the two types of line chargers we're going to look at. On the left, we see a screw pump, which is a very traditional type of line charger used globally in the cement industry. It's a continuous system in that the material enters the top of the screw pump, transferred through the pump into the convey line and onto the destination as a continuous stream. The alternative we're going to look at is a pressure tank system using two pressure tanks operating in parallel, each one being a batch process, but together they actually form a near continuous system on the same basis as the screw pump. And Entering that information into PneuCalc simply means you're looking at a different peak conveying rate. And Colin will cover that during his demonstration that's going to start right about now. So I'll pass this over to Colin, and he can begin his presentation.
Thank you very much, Jack. I think you guys probably see my screen. So again, thank you for this very good introduction to the PneuCalc software. I think now we understand the basis of our application, and now we can start doing some calculation in PneuCalc on this system. The first screen that I'm showing is the project tab in PneuCalc. I'll go quickly over it, but basically this is where you enter your project related information, who designed, who made the calculation, who checked it. You can leave comments for future reference when you reopen the file in the future, or if you need to leave any comments or traces of assumptions that you've made, it's a good place to put all this information in. But I'm going to jump over this tab and continue with the material tab, because I think we're all here to see some calculations. So quickly, before I start, just explaining how this tab works. Basically, you can, as you work in PneuCalc, you're going to generate your own material database. So you can add a material into database simply by clicking the add button right now, right there. And PneuCalc is going to generate a generic material for you. And then what you need to do is go into this material and then enter the different material characteristic for your specific material. And as you do this over time, you're going to generate your own database that you can always reuse for future calculations. So you don't have to enter the same material again and again in PneuCalc. It's always available. And you can also share this database with colleagues or friends or even family members if they're into pneumatic calculations. So for our demonstration this morning, we are going to select cement. And as you've seen, I've already inputted the material characteristic that Jack presented earlier. And I've also just checked over here the box on the side of the abrasive property for the chemical properties. So this is not going to change the calculations, but now the material is tagged as being abrasive, and this is going to show downstream in the reports that we're going to generate. And it's a good thing to have it tagged as a reminder, as an example where you're going to work with your component suppliers to make wise decisions about the type of construction materials that you want to use for this material. But again, knowing that this material is abrasive, and I'm just linking to what Jack presented, we want to carry this material to a relatively low speed in our system. A great thing that this material tab does for us is that it automatically generates the Geldart chart classification of our material for the minimum, the average, and the maximum particle size. And this is a great tool just to also guide us in our decision-making process. So we see that this specific material falls into the classification A for Geldart chart, which is a material that fluidizes very well, that likes to be conveyed pneumatically. And this is, again, going with following our thought process that this specific type of material, a Class A Geldart chart, is a good choice for a mixed mode of conveying. Again, just a nice tool to have, and we could chat about this tool for many minutes, but it's available in PneuCalc. It generates the graph automatically, and we can talk about this tool in other trainings that we do or other future webinars. The next thing that we need to select is what gas are we going to use in our pneumatic system. PneuCalc comes loaded with air and nitrogen. So if you're working on an application where you have a combustible material, you might want to use nitrogen to prevent deflagrations. But in our case, we're going to use air simply. And again, you can generate additional gases if you want to try other ones, or if you want to create special gases, very hot air or very cold air, you can generate those gases in your database, and you'll have them in the future as well. All right, moving to the geometry tab. This is where we generate the layout of our conveying system. Our layout is composed of different components, basically pipe and bends, and we stack them over here in order to produce our layout. And what we see in the bottom portion of the screen is what we call the unfolded conveyor layout. So it's basically a 2D representation of the conveyor or the conveying system. So if you were to stand on the ground and you would have the piping in front of you, you have your vertical axis over here in the y-axis and your horizontal distance on the x-axis over here, and the conveyor has been unfolded in 2D in front of you, basically. The green point is your material injection point, where your line charger is. Your red dots are your elbows, and the blue lines are basically the piping that you've generated. So referring back to the layout that Jack presented, we have our material injection point over here, our line charger. Then we have a small horizontal pipe segment. Then we go up vertically for a few meters. And then we go horizontally near our silos with a 90-degree bend in the horizontal plane. And then we go up vertically towards the top of the silo. And what's missing right now is the last horizontal segment to carry the material up to the target box at the center of the silo. So the way that we do this in NewCalc is quite simple. We have a default diameter that is set to DN150 for our piping elements. We have access to imperial or metric libraries. So we're going to go back to metric 150, and we are going to drag a bend right here in our layout. We see it appearing in the unfolded view, and then we're going to drag a pipe, and this pipe, yes, it's horizontal, and I'm going to change its length to 13.75 meters. And that's it. Our layout is completed, and we are now ready to run some calculations on this system. So I'm now going to switch to the main page, which is the core of the calculations in NewCalc. There's like 3 different windows over here. There's the calculation window, where we have some tools to adjust the parameters of our system. Mostly, we're going to look at the airflow over here and the pressure in our system. Those are 2 key parameters. We are also going to, we have to make a final input before we can run the calculation, and this is the saltation velocity. I'll go back to that in just a few moments. I want to present the right the graphic that we have on the right-hand side, which shows the pressure of the system in relationship with the volumetric flow rate that is in the system. So this is a great graph to understand where you are located on that curve, and it's a great guide to adjust your flow rate and your pressure, because they're related together, to really fine-tune your application. And finally, what we have here on the bottom of the screen is all those piping segments that we have entered in our geometry. They are over here, and this really is the output of the calculation. So for every segment of pipe and bend, there are some outputs: the pipe pressure, the velocity of the material, calculations on the vertical segment to see if there is line refluxing. But what also is a very nice output to look at is the conveying mode, which is shown over here. So for every segment in the pipe layout, you know what is happening by looking at this column over here. And of course, then you go into more details if required. So just before I hit the calculate button, I'm going to finalize my material saltation velocity. The saltation velocity is the velocity in the system at which, if you reduce it slightly, your material is going to start to fall from the airflow and start to hit the bottom of the pipe. This is a material property that is very important, and it's the in the core of the NeuCalc calculations. So NeuCalc comes with different algorithms to calculate theoretically this saltation velocity. So these are all good tools if you don't have this value at hand. What we did for our cement is that we have tested it in a lab to get a very accurate value for the saltation velocity. And this is what we're going to use this morning. We're going to, or this afternoon or evening, but we're going to use 8.64. And this is something that we do at Hatch, and we strongly encourage everyone that is using NeuCalc to do is once, when it's time to finalize your system and purchase your component, we encourage users to get the material tested to be sure that they're working with the accurate material properties. All right, enough talking. Let's jump into this calculation. So I'm going to hit calculate, and now let's look at the different outputs. We have in red here, we have a very high conveying pressure. We had the target of 175, and we are about over 1,000. So this is too high. So we're gonna need to reduce our system pressure. And if we look at our conveying mode, we see that we start in the dense phase at the beginning of our system. As the speed increases as we move along the system, we start hitting the mixed phase around roughly half of our system. And then as the speed increases again, we hit the dilute mode of conveying. So what we need to do is try to control our speed in order to stay in the mixed mode of conveying from beginning to end. So the first thing that I'm going to do is I'm going to increase the pipe diameter of our system. 300 tons per hour as our instantaneous capacity in a 150 millimeter pipe over this length is requiring too much pressure, and this is something that you'll get familiar with those numbers as you use the software. So what I'm going to do is, the first thing I'll do is I'll increase my pipe diameter to 400. So I'm using what we call the master override tool here. When I click override, all my different piping elements are now overrided to 400 millimeter. So let's hit calculate again and see how this impacts our system. So our design pressure is now at 185. So we have accomplished one of our target, which was to reduce our pressure. We're not there yet in terms of we still need to reduce it a little bit. And we see that we still start in dense phase and finish in dilute phase. So one of the next thing that we are going to do is that we're going to increase our airflow in order to increase our velocity in our system and try to start our conveying in the mix mode. So I will change my volumetric flow rate from 1.2 to 1.64, 65, sorry. I'm going to hit calculate again, and let's see what happens. All right, so we're making progress here. Our design pressure is now below our maximum target, which is great. And we see that we start conveying in the mix mode and we finish in dilute mode as, again, speed increases in the system. So what we need to do now is we need to control the speed or reduce this velocity of our material in the last segment of this system. So the strategy that we're going to use to do that is that we are going to increase our pipe diameters locally over here. where the speed or the velocity of the material is too fast. So I will not use the master override tool because this is going to change. It would change the diameter of every pipe in the system. So I'll go back to my geometry tab, and then I will change one by one the diameter of the pipes where we hit dilute phase. There's no right and wrong over here. It's basically trial and errors and experience, which is going to guide you in order to do this pipe stepping. So we need to start somewhere, right? So we have our system has a nominal diameter of 400. So I'm going to start stepping my line using 450. So I'm going to change that right here. So bear with me, we need to do this one by one and make sure that we don't make mistakes. Then I'm going to switch to 500 millimeter for the remaining components of my system. 500, this one over here, I'll change it to 500 too. And the last one also, we will change it to 500. So we start at 400 in our system, then we switch to 450, and then we end up with 500 millimeter pipe. Let's go back to our main page and hit calculate and see how this affects our results. All right. Again, we're making progress. We are mostly in mixed phase during the whole system, except during the last portion of our, the last segment of our system. So what I'll do, I'll go back right here just to show you. I'll change this diameter from 500 to 550. And then hopefully we should reduce the speed over here and continue our conveying in mixed mode during the whole, for the whole system. So we have accomplished what we wanted to do, and our pressure is at 134, which is below the maximum pressure that we had set for our screw pump. So now if we were to look at this exactly same example, but using a dual blow tank line charger, how would we do that in NeuCalc? First, we need to change our capacity because our system needs to produce or to handle an instantaneous capacity, nominal capacity, sorry, of 300 tons per hour. NeuCalc works by using the instantaneous capacity. So what is the maximum instantaneous capacity that the system needs to handle? With blow tanks, as we alternate from one to another, there's a small loss of efficiency because during that brief moment, the pneumatic system is actually not pushing material into the pipeline. So we need to increase our instantaneous capacity to make sure that when we push material, we're going to push a little bit more, and over a period of an hour, say, we're going to get 300 tons per hour. So this factor typically varies between 5 to 15%. So we're going to use 5% this morning. So we're going to change our instantaneous capacity to 315 tons per hour. And we're going to hit calculate. It didn't change drastically the result. The material to gas ratio is a little bit higher, but other than that, there's no drastic change on our system. The reason is that we didn't change our volumetric flow rate and we didn't play with our piping so far. So we're going to do that in just a moment. But with using the blow tanks, we're going to be able to work at a higher pressure, right? And we're going to be able to use a lower flow rate. And in turn, this is going to allow us to use a smaller pipe diameter and keep the same material speed in our system. So I'm going to go to user preferences and change my required design pressure from 175 kPa, which was the pressure for the screw pump, to 310, which is a typical maximum pressure for blow tanks. So I will do that like that. And basically what I'm saying to NewCalc is, if my pressure gets below 310, please highlight this in red so that I can take care of that. So I've set out my maximum required pressure, and then I will reduce my pipe size. So I'm going to use my master override tool here and change my system from a nominal system of 400 for the screw pump to about 250. I'm going to override my piping geometry and press calculate again. And now let's look at what we have. We have a system at 315 tons per hour. It is operating at a flow rate of 165 cubic meter per second. Our pressure is at 355 kpag, so it's slightly over our target of 310. We start in mixed mode of conveying, and we hit a dilute phase about roughly at the half position in our system. So what we will need to do again is we will need to do some line stepping over here in order to reduce our speed. Just before I do that, I want to show you this graph over here, which represent the pressure in our system in relationship with our volumetric flow rate. So we are at 165. We are somewhere over here. And what this graph is telling us is that if we reduce our flow rate, we are going to increase our pressure in our system. So just to show you that, I will change it over here to 1.42. I'm going to hit calculate, and our conveying pressure is at 355. If I calculate, we are at 371. So what I've done by reducing my flow rate, as predicted by the graph here, is that I've increased my pressure. But I'm okay with that, because what I will do right now is I'm going to increase my pipe diameter here, and in turn, this is also going to reduce my pressure. So let's have a look at how we can do that. I'll go back in geometry, and then as we did previously, I'm going to start stepping my line. So we are at 250 nominal pipe diameter, so I will start increasing my diameter to 300, like so. Then I'm going to switch to 350 as we continue to move downstream in the conveying system. And finally, I'm going to use 400 millimeter pipes. We just need to be careful here, make sure we don't make mistakes. It wouldn't be the end of the world. If we make mistake, we can easily go back, correct them, and see how it affects the calculation. And in all honesty, again, this is based on trial and error experience, and it's not the first time that I do this very example. All right, so we have stepped our line, so let's hit calculate one more time. And we are almost in the mixed mode of conveying for the whole system. Let's have a look at our detail page, which shows calculations done at every meter in our system. I'm gonna just go down at the very last portion of our pneumatic system, and we see that we are in mixed phase or mixed mode of conveying until the very, very end of our conveyor, until we hit that target box, the last meter of conveying. So we are okay with that. It's not, on this particular example, this would be totally acceptable, and we would be okay with that system design. So this would be a valid solution for a blow tank application on this same system. So just before I give the floor back to Jack, I want to show a last feature of NewCalc, which is the report. So once you're finished with your calculation, you can generate an Excel spreadsheet for your your file, your NewCalc file. So basically, everything that you did in NewCalc is now exported in Excel, and you have access to all this data from the Excel spreadsheet to then work on any other type of documents that you need to create. Data sheet specifications, you can exchange information with vendors. You can also use Excel to generate additional calculations or graphs or whatever, and Jack will show you that in just a moment. What I wanted to show you too was the component tab, where this is a work page where you are going to finalize the component selection. So if we look at an example, the gas mover, NewCalc doesn't take into consideration the clean air pipe of the system and any leakage in the system. So this is where you would input those values to get the final specifications for your components. Okay, all right. I think this is enough out of me. So I will now give the floor back to Jack. I will stop sharing my screen, and Jack will summarize what we just did in NewCalc this morning.
Thank you, Colin. Great presentation. Good detail of information for our participants. I did notice while you were speaking, I glanced at who our current participants are, and we do recognize many of you are current NewCalc users. So we're glad you joined in for some refresher information, and maybe you've learned something new today as well. Colin mentioned that one of the advantages of NewCalc is that it does export the calculated results into Excel, where you can use it to generate additional information to analyze the results of your calculation. And on the slide you're looking at now, we've actually used the information from NewCalc to have Excel plot a velocity profile of the system for both the screw pump solution, which is shown in blue, and the pressure tank solution, which is shown in red. And all throughout the calculation, you notice that Colin was always looking at the summary chart and the color which is being shown on the right side, whether it was blue, green, or yellow. And those color and that designation of the mode of conveying is determined strictly based on the velocity of the system in each of those segments of the convey line. So we know that velocity is very important, and more so the velocity profile, which is the difference between the velocity at the pickup point, which is always the lowest in a system, and the velocity at the discharge point, which is typically always the highest in the system. So you can see on this chart that Colin was able to step the pipe in both cases with the screw pump and the pressure tank system 3 different times to get larger diameters so that our total velocity profile stayed in a band in which kept us in 2-phase flow. Now the next slide takes this same chart, but it adds a little bit more information. It actually shows you where the dense phase portion of the analysis would have taken us with that large blue section, and where the dilute phase or the green portion of the calculations would have taken us had he used lower velocities, lower air volumes, or higher air volumes respectively. So basically that zone in between the green and the blue is the yellow zone, or the 2-phase regime that we wanted to stay in. And by using those pipe selections that he chose and the corresponding air volumes, we were able to achieve that result. Now you notice that the shape of the curve is what we refer to as being a sawtooth profile, because it has a distinct section where the velocity is increasing, and then you can see that drop of velocity, the vertical line, indicates every point along the line where a step was made in the system. And you can look down at the x-axis, and that tells you the location or the distance from the pickup point at which those step points occurred. And it's very critical that you step the line at the right location, not just to reduce pressure drop, but that you always maintain sufficient velocity at the step point so you don't drop into that dense phase mode. And you'll see that in this solution, we're in a range of about 7 to 10 meters per second for that complete band of being in the two-phase flow. If you look at the next chart, the next profile, it looks similar, but this is plotted as position along the x-axis and pipe diameter along the vertical axis. And you'll see, and you noticed in the demonstration, Colin jumped in pipe diameters in 50 millimeter increments. One of the advantages of NeuCalc and the fact that metric piping availability has many more intermediate pipe diameters available than does the US system of pipe. So ideally, if we could have a velocity profile in our system that was near to be a straight line, that would basically be a constant velocity system. And then that would really be the best way to mitigate any abrasive wear, because we're always running at the lowest velocity. We can't achieve a perfectly straight line. And you see that the step points that, based on the diameters Colin chose, do keep us in that 7 to 10 meters per second range. But had he chosen some smaller incremental steps in the piping, instead of going from 4 to 450, for example, let's say he would have went from 4 to 425, those number of steps may have been more, and the velocity profile may have been more, but in the real world, you don't want to be stepping pipes every 20 or 30 meters. So there's a balance between the velocity profile you achieve versus theoretical and the practicality of installing the system in the field. You also need to keep in mind that in Colin's example, when we did the screw pump example, he ended up in a 550 millimeter diameter line. One of the concerns you need to be aware of is that when you get to your destination, and typically in the cement industry, when you convey to a silo, you don't convey to just one silo. There's typically a bank of storage silos. And you have to keep in mind the availability of convey line diverter valves so that you don't design a system with a pipe large enough to give you the velocity you want, but then you can't get commercially available diverter valves. So there needs to be a mix of the theoretical and analytical calculation within NeuCalc, as well as the availability of components to suit the design that you come up with. And in this case, you can see the various diameters that he chose. So at this point, we've given you a lot of information. We've shown you a lot of things. Now's the opportunity where we're going to take to answer some of the questions that you have submitted during the presentation. So I'm going to turn it back over to Colin, who's going to be the moderator for that question and answer period.
Yep. Thank you, Jack. We do have received a fair amount of questions. We're going to try to go through them all together right now. If we don't have the time, we will make sure to reply in writing to everyone that has taken the time to ask a question this morning. Jack, we have a question regarding the system design pressure. How do we justify that the design pressure is optimum, or how do we know whether the design pressure is acceptable?
The design pressure of the system has to take into account primarily the line charger capability, which is the piece of equipment that's putting the material into the pipeline. In this case, in your example, you had set limits, or not, you didn't set limits, you chose a maximum design pressure on the basis of the 2 line chargers that we selected. We know that the screw pump typically has a limitation in maximum line pressure because the horsepower of the pump is based not only on moving the material through the pump in almost like a screw conveyor fashion, but more importantly, the back pressure that the pump has to deliver against increases horsepower. And there's a point in any system design where that horsepower just becomes an exponentially large number, and it exceeds the limitation of the screw pump. So that number you would get from whatever vendor of screw pump you may be utilizing would give you that number as being the design limit for that piece of equipment. With the pressure tanks, they have the advantage of basically not having that large motor that a screw pump has. It's only dependent upon the line pressure and the fact that these are coated pressure vessels. They can be designed basically for any pressure. But again, you're going to be utilizing either plant air as your air supply, which is normally a 6-bar supply pressure, but you're going to run your system normally in that 2 to 3 bar range. So that's how you set the original design pressure target. Then compare the calculation of NeuCalc to stay in that range.
Great answer, Jack. Thank you. I will try to answer the next one. How similar is the calculation result to the actual measurement? If not, please explain what needs to be improved. So NeuCalc is a calculation tool, right? And one of the key parameters in NeuCalc are the material properties. So as I explained during the webinar, we strongly encourage users when working on an application that will have a real life construction, right, to test the materials in a specialized lab in order to be sure that they have the accurate material properties. The same material with a different particle size distribution or a different moisture content is going to act differently. Also, during those lab testing, you have the opportunity to run your material in a small closed loop system and get the result from that. And in NeuCalc, there is a calibration factor that you can use in order to fine-tune the calculation to match specifically an application or a bench scale test. This is also very helpful when you're troubleshooting an existing equipment or you want to make changes to an existing equipment. You have the opportunity to adjust the NeuCalc calculations to match closely the real-life system by tweaking the calibration factor in NeuCalc. So I hope this answers your question. Jack, would you like to add something to this, or?
Yes, I would. I would just like to say that calibration factor, the default value in NeuCalc, if you don't change it, is 1. And by design, that has a slight margin of safety on the order of 10% to the system design. So you're already starting off with NeuCalc is giving you a safe, slightly conservative answer. And the other point is that if you do determine what your calibration factor really is by utilizing NeuCalc to analyze your existing system, you can put that number, you can change it for that material, and your database will always have that number in it for that material. So in the future, if you go back and make changes, you've already now are working with the corrected or with the adjusted calibration factor.
Yeah, thank you. Great addition, Jack. I think we'll have time maybe for another one. Is the design pressure displayed in NeuCalc the pressure the blower selected must be sized to? So maybe we got this question before I showed the work page in Excel. So the answer is no. The pressure that is shown in NeuCalc shows the system pressure in order to from the material pickup point to the material discharge point. To that, you basically need to add any pressure drop related to the clean air piping, leakage, if you have a filter in your system, and the Excel spreadsheet workpage is the tool that we supply with NewCalc in order to do that. And this is, as I mentioned, helpful to select or to specify, your line charger, but also your filtration system, as well as your blower package or your pressure system. Okay, we do have other questions, but unfortunately, we will not have the time to answer them right now. I need to give the floor back to Manoj for the closing word on this webinar. But I want to thank you, everyone, for your questions, and we'll reply in writing.
Well, thank you, everyone. I think for your questions and time, they were really interesting questions. Thank you, Jack and Colin. It was really a wonderful effort where you have explained each and everything about NewCalc software. We hope everybody online, you have also enjoyed this. If you find that you still have some questions which are not answered, or if you want to connect with us, you can always see our email address in the slides. We would like to convey our thanks again for your time. And I just wanted to remind you, don't forget to check out our NewCalc trial. It is free. And further, you can also use our promo code that we have shown in our slide, where you will get 20% on NewCalc licenses and training. So please utilize that. And further, please remember, as I have told you, recording of this webinar will be made available. So now, as we are reaching towards the end of this webinar, I would urge everyone to please take the feedback survey. It's really very important for us because it will provide us the feedback whether we have met your expectations or not, or how we can improve in our future endeavor. So I think with that, I just again want to thank every one of you who have spared the time and joined online. Thanks again, and have a good day and stay safe. Thank you.